All right. We finally get to start new reactions. I'm sure you guys were missing chemistry over break. All right. So this term, we're going to be covering a lot of reaction mechanisms. I really recommend that you get some colored pencils. It'll make your life a lot easier. If you don't have them already, you can bring them in. If you've got colored markers or prefer markers, those work too. But let's do a little bit of review from last term. So I'm going to give you guys a reaction. And I'm hoping that you guys know this. We're going to take concentrated acid and heat, and we're going to react this with cyclohexanol. What will our product be? Cyclohexene. Just like we saw in lab, we'll do an elimination reaction. Will this likely be E1 or E2? It'll likely be E1. So anytime we see acid that's concentrated in heat, it'll tend to favor the elimination reaction. So if we think about these elimination reactions, it results in a new double bond. I'm not going to go over the mechanism for this, but if you want, you can review your old notes and cover it that way. The reaction is favored at high temps. Why is that? Does anybody have an idea? Why don't we run this reaction cold? So activation energy could be a big part of that. What do we notice about moles here? It goes from 1 to 2. Yeah, we start out with 1 mole and we're going to 2 moles. So we're increasing the entropy of the system. So delta S is positive. That means that this is favored by high temperature conditions, right? Addition reactions look pretty similar to this. So let's take a look at some addition reactions. So this time I'm going to start out with cyclohexene. And I'm going to add in some water. And again, I'm going to add in some acid. But this time, we're going to form cyclohexanol. Looks pretty similar, right? We're just going in the reverse direction. So that brings up a lot of points for addition reactions. They're just elimination reactions in reverse. So in this case, we go from a double bond to a single bond. We're adding things across that double bond. And in this case, the reaction is favored at lower temperatures. At low or moderate temps. In this case, we don't want to apply too much heat because entropically that would be disfavorable. We're going to only 1 mole as opposed to the 2 moles of starting material. All right, so let's take a look at our first addition reaction. And this was one you guys have actually already seen before, or actually similar to one you've already seen before. And this is called hydrohalogenation. So I'm going to take a really simple alkene. What would we call this alkene? Wouldn't be ethene. We've got 3 carbons. Propene. Yeah. And in this case, we could say 1 propene, but really that's the only option, so people normally just call this regular old propene. So we're going to take propene, and we're going to react this with hydrobromic acid. In this case, what do you think the nucleophile is going to be? The pi bond or the HBr? The pi bond. Nucleophiles are always the site of electron density, so it can either be a lone pair, it can be a pi bond, or it can be a formal negative charge. So in this case, our nucleophile, this pi bond, is going to attack this proton. And are we done?
No, it breaks the bond.
Yeah, we've got to break the bond to the bromine. And we've got two potential options. We've got one where that hydrogen can be installed to that center carbon, or alternatively, we could have one where the hydrogen's installed to the carbon on the right. Which of these products do you think is going to be more likely? The second one. Why do you think the second one's more likely? Yeah, exactly. So if we look at this one, this would result in a primary carbon that's not likely. This is a secondary carbon, which is much, much more stable. So if we think about it, it's very similar to what we've seen before. We've got a nucleophile. And the nucleophile for addition reactions is always going to be a double bond, and it's attacking some sort of electrophile. All right, so we're almost there. The byproduct of this reaction is Br minus. So intuitively, what do you think will happen? Yeah, we've got another nucleophile and we've got a carbocation. That's an electrophile. So this bromide can just attack our carbocation center. And it can attack from the top face, meaning that bromine becomes a wedge and this hydrogen becomes a dash. Or what do you think the other option is? The bottom face, right? So it can attack from either side of that carbocation. We talked a lot last term about how carbocations are trigonal planar with that empty p orbital sticking up and down. That means the bromide can attack from either lobe of that p orbital. So when we look at this, we'll get two different products. We'll get one where the bromine is underneath, and we'll get one where it's on top. What's the relationship between these? Ah, they're identical, right? There is no stereocenter in this molecule. So now you guys are probably like, this is why he was irritating us so much last term, trying to identify these. Because these are the exact same molecules. Yep.
So with the primary carbocation, is that so rare that it's not?
You won't even observe a minor product. In this case, it'll always favor the more stable carbocation that can be formed. All right, so let's make a few notes on this. So in this case, with halogenation or hydrohalogenation reactions, the halogen always adds to the more substituted side of the alkene. What if we wanted this reaction to go in reverse? What could we treat it with? Heat? So we could apply heat, but we need something else. How could we go from our final product, that 2-bromopropane, all the way back to propene? An E2 reaction. Now we've got a good leaving group. We would have to apply or give a very strong base to the reaction, something like sodium hydride, and it would drive the reaction in the reverse direction. So just like we saw on the previous page, these reactions are exactly like what we saw last term, but in reverse. All right, and we also have new terminology we have to remember. So last term we talked a lot about Markovnikov and Zaitsev and Hoffman. Sorry, I'm getting ahead of myself. Zaitsev and Hoffman products. In this case, we have to talk about regiochemistry using different terms. So we call this Markovnikov addition. Markovnikov addition just means that you're going to add whatever it is to the more substituted side of your alkene, not the less substituted side. And one thing we've got to watch out for with these reactions is we have to watch out for stereoisomers. In the example I showed you here, the two theoretical stereoisomers are the same molecule, but in some cases they're not, so you have to be aware of that. If we had a more complicated alkene, we would run into a set of stereoisomers. All right, so I'm going to give you guys an example problem, and I want you guys to work with the person next to you to try to solve this. And I want you guys to try to help me figure out all of the potential products for this reaction. All right. So we've got this alkene. Again, we're going to do a hydrohalogenation reaction with it. So we've got to first assess where the carbocation will form. For those of you that are stuck, what's the first step? Does anybody have a hint? Yeah, our nucleophile is going to attack our electrophile, kick off our bromine. Then we could draw two potential products. We could have one where our hydrogen adds to the right side of the alkene and our carbocation forms there. Or we could have one where our hydrogen adds to the other side of the alkene. Which one's more likely? The one on the right, because it's a tertiary carbon, not a secondary carbocation. So this will be our intermediate. We also have bromine floating around, or sorry, bromide floating around. So what will the next step be? Oh, I'm forgetting a carbon here. There we go. It'll attack in, and it can attack from either that top face, or it can attack from that bottom face. So let's think about both of these products. Let's do the top face one on the left. So we'll call this top face attack. That means the bromine will be a wedge, and this methyl group will be a dash. And then we could have one where we attack from the bottom. And if we do this, our methyl group is going to be a wedge, and our bromine is going to be a dash. What's the relationship between these two? Are they the same? Are they different? If they're different, how are they different? We've got some debate. What do you guys think? Are they stereocenters now? Yeah, they're stereocenters. If we look at this position right here, we've got an ethyl group coming off of it, we've got a propyl group coming off, and we've got a methyl group and a bromine. Those are four different substituents coming off of one carbon. There's no internal plane of symmetry, so that is a stereocenter. In this case, if we look at these two compounds, they have inverted stereocenters. So what would the relationship be? Enantiomers. In this case, do you think one enantiomer will be preferred over the other? Not really. That carbocation intermediate's planar, so there's really no preference for one over the other. What do we call that if we get a mixture of enantiomers in equal proportion? Racemic, exactly. This is great. You guys are remembering. You didn't forget everything over winter break. It was too short. All right, so now let's take a look at regiochemistry again. Regiochemistry describes the position of attack. So in this case, we said if we've got something like propene plus HBr, actually I'll put HBr over the arrow, we'll get bromine to add to the more substituted side of the alkene. And this is called Markovnikov addition. Markovnikov addition means that in this example, we're going to add to the more substituted side of the alkene, not that less substituted side. So you always prefer that position for your halogenation. And this is aptly named after the chemist who discovered this reactivity or this regiochemistry. However, there was a problem. Occasionally, he would run this reaction and the bromine would add to the less substituted side of the alkene, meaning instead of the side with one substituent coming off, it came off this side with no substituents. And this was really, really frustrating for him. And he bought hydrobromic acid from a variety of different suppliers to try to figure out maybe it was an impurity in the hydrobromic acid that was causing different regiochemistry, and he was correct in that. In fact, there's a very specific impurity where we've got a new functional group, oxygen, directly bound to another oxygen. Does anybody remember what this functional group's called? It's a peroxide. Similar to an ester, but we've now got a carbon-carbon, or an oxygen-oxygen bond, which is very weak. It likes to do radical chemistry and cleave apart. So in this case, he noticed that if you add peroxides to a hydrobromination reaction, you actually get different regiochemistry. And he coined the term anti-Markovnikov reaction. Yep. So OOR is coined for a peroxide. This could really be a variety of different peroxides. Oftentimes people will just toss in a little bit of hydrogen peroxide. We will discuss the peroxide mechanism in chapter 11. And this only works with hydrobromic acid. If we try to do the top reaction with hydroiodic acid, you can get it to work. Same with HCl. But the anti-Markovnikov addition will only work with hydrobromic acid and peroxides. To be perfectly honest, I'm still not entirely sure why that's the case, and I want to read more about it. But the key takeaway is if you're running a reaction with an alkene and plain old hydrobromic acid, the bromine will add to the less substituted side. However, if you do that same reaction with peroxides, it'll add to the less substituted side. All right, I've got another problem for us to work on. This is going to rely on your skills from last term. We've got this alkene. And we're going to treat it with hydrobromic acid. This time, no peroxides, just regular hydrobromic acid. First step, double bond's going to attack. Is the hydrogen going to go to the carbon on the left or the carbon in the middle? Middle. Okay. That means we've got a secondary carbocation and we've got bromide around. So if we've got bromide around, so the hydrogen, I'm not drawing it, but it's still coming off of there. It's an assumed hydrogen. So now we could have this bromide attack from this face or that face. And this could result in two different products. you could have bromine coming out of the page, whoops, and the hydrogen here going back. Or you could have your hydrogens coming forward and this bromine going back. All right, do you think that's going to be the major reaction pathway? Does anybody see something that they're itching to do? Rearrangement, right? So if we look at this one, we've got a secondary carbon, or a secondary carbocation. However, can we do a hydride shift?
No.
No, if we did a hydride shift, we'd go to a primary carbocation, so that's not likely. But we can do a 1,2 methyl shift. So in this case, all we need to do, I'm going to change arrows here, is move this methyl group over to that carbon. Now we've got this really nice tertiary carbocation. And we've got bromide. In this case, does it matter which side of the carbocation the bromide attacks? No, because it'll only give you one product out of this reaction. So now if we draw our products for this reaction, we'll get this product. All right, which one do you think is going to be our major product? The two on the left that are racemic, or the one on the right? The one on the right. So in this case, this will be our major product. And these two will be our minor products.
What is the reason?
The reason being that the carbocation intermediate for our minor products is so unstable that it will spontaneously undergo a 1,2 methyl shift, form that tertiary carbocation, and then complete the addition reaction. It's just like last term. Anytime you can spot a rearrangement, it will likely occur, and that will be your major reaction pathway. Does that make sense?
So the H can either go where the H is now, or it could. So like the plus can be where the H is now, or it can be. Do you know what I'm talking about?
So are you asking, do we install the hydrogen here
Yeah.
or here?
Yes.
Anytime we do the reaction, we want to form the more stable carbocation. So by adding it here, it will be on the secondary position rather than the primary
Yeah.
position.
Okay.
So that's always the first step, but after that step, you've got to watch out for potential carbocation rearrangements.
Okay.
Carbocation rearrangements, just like we saw last term, show up over and over again. So carbocation rearrangements. Sorry, it's kind of squeezed in there. Whoop. All right. Yep.
So this is the major product only because that's the third degree carbocation and that's the second.
Exactly. We always want to go through our more stable carbocation intermediate. All right, so let's jump to our next reaction. We're already one reaction into the term. This one's pretty similar, though. So you guys will start to see that when we cover these reactions, they all look similar. So this time we've got an alkene. We've got water. We've got catalytic acid. And we've got to determine the product. So in this case, what do you think the first step of this reaction will be? What's the fastest reaction in chemistry? Acid base. All right, so we've got our water, and we've got our acid. So this is going to be step one. Oop. Shoot. So step one will just be a proton transfer. We'll protonate our water and form hydronium. Okay, now we can deal with step 2. It does not like this. Step 2, we've got our hydronium that's formed. And we've got this propene. So what do you think this propene can do with that hydronium?
Take on nitrogen.
Yeah, so let's actually draw out the hydronium with all of its bonds so that we can show the bond transfer. So in this case, we can have this pi bond attack it, just like we saw in the last reaction where it grabbed the proton from the strong acid. And then we need to break this bond. Okay, and will our hydrogen add to this side and form this carbocation, or will it add to this side and form that carbocation? Which one's more likely?
The left side.
The left side. So in this case, let's not even bother drawing the other possible product because it's so unlikely it just simply won't occur. Okay, our byproduct from this reaction is going to be water. It's our conjugate base. What do you think could happen next? Yeah, water has a lone pair, so water can act as a nucleophile. And it can add from the top face or the bottom face, just like the bromide we saw before. And so we could end up with 2 different products. The oxygen has a positive charge now that it's added in, so it could be coming from that top face. Or, oops, sorry, this should be a wedge. Or it could be coming from that bottom face. What's the relationship between these two? They're identical, so we don't have to worry about drawing them both. You could draw it 1,000,000 times for all I care. You'd just be wasting your time, right? So what do you think the last step is of this reaction?
Water attacks.
So we could have more water around in solution that could do what? Proton transfer. So we've got potentially extra water around in solution. This can come grab the proton. And I'm not going to draw both potential products because it doesn't really matter. So if you notice, we regenerated our hydronium in this case, which again goes to show that this reaction only needs a catalytic amount of our acid source, not a very strong acid, just a small amount of catalytic acid. So let's make a few notes on this. It's very similar to hydrohalogenation. But with alcohols. In this case, I used water. We could use something like methanol and form an ether, or we could use ethanol. Any sort of alcohol will work for these reactions. I just chose the simplest alcohol, which is water. The acid used is catalytic. We don't need a full stoichiometric amount since it's regenerated in the reaction. And the reaction proceeds faster with a more substituted alkene. Why do you guys think that's the case? Why would the substitution pattern of the alkene matter? What do you think?
What is that?
So let's say we've got a primary alkene, or sorry, a monosubstituted alkene versus a tetrasubstituted alkene. Why would the tetrasubstituted alkene proceed at a faster rate? Yeah, it forms a more stable carbocation. So typically with these reactions, you won't see them occur very readily on alkenes that aren't substituted. And then we also have to watch out for stereochemistry. And rearrangements. All right, so now the question is, why would we observe the reaction where the alcohol is adding in rather than the reverse reaction where elimination occurs? And there's a couple ways we can control this. So how do we favor addition versus elimination? What's one way we can favor addition versus elimination? Temperature. So just like we saw at the start of class, entropically, lower temperatures favor addition reactions. And then let's think about this from another point of view. So I'm going to draw a reaction, and we've got water. In some cases, we can form cyclohexanol through an addition reaction, and then in other cases, we can go from cyclohexanol straight back to cyclohexene. In the forward reaction, what should we use for an acid? Should we use a strong acid, a weak acid, a small amount of acid, a large amount of acid? What do you guys think? We want to use a strong acid, but in this case, we really want a lot of water around in order to push the reaction forward, right? So if we have a lot of water and acid, we simply just describe it as a dilute acid, right? So if you go into a chemistry lab, you can grab a bottle of dilute acid or concentrated acids. For addition reactions, we typically want to use dilute catalytic acid. Again, going back to the Le Chatelier's principal idea of the more reagent you add in, the faster the reaction will go. All right, if we want to do the reverse reaction, what should we do? Not a strong base. A strong base would deprotonate our alcohol. Strong concentrated acid. So what was the acid we saw most of the time in our book? Phosphoric. What's another one we could use? Or sulfuric. So typically when you're doing the elimination reaction of these, you would treat it with really concentrated sulfuric acid like we did in lab, or phosphoric acid, and we would also apply heat. So I think that's where we're going to end off today. Tomorrow when we come in, we're going to talk about a few reactions, and I'll give you a challenge problem. Make sure you grab a problem of the day on your way out, and that will be due tomorrow.
Good question.